Hello, and welcome to another lesson for supporting quantitative educational research methods. In this lesson, I'll be talking about quantitative measurement in educational research. Okay, let's get this started. So, the first thing I wanted to talk about were the different types of quantitative data. Sometimes these are referred to as different types of scales. The first is nominal data. Well, this is just your categorical data. So, things that can be counted or that you can figure out proportions for. So, for example, the proportion of the class that identifies as male, or the proportion that identifies as female, or the proportion that identifies as being racialized or not, or the proportion that are coming from different geographical locations. Those would be examples of nominal types of data. The second is ordinal, and the word gives it away. This is ordered data. Now, the key here is that the difference between the numbers that represent the points on the scale aren't always the same. So, for example, socioeconomic status, low, middle, and high. You can't really declare that the difference between low and middle is the same as the difference between middle and high. Similarly, level of education, even level of agreement. So if you've ever completed a agreement scale where you've got a bunch of statements and you're being asked to indicate your level of agreement, in fact, those are ordinal scales because you can't really say from one person to the next that the difference between a 4 and a 5 or a 2 and a 3, for example, are actually the same. But you can say that a 4 would be considered ranked higher than a 3. So it does facilitate ordinal scales, ordinal data does facilitate the ability to compare people in terms of their rankings. Moving to the next one, interval data adds the ability to talk about the difference in how much of something you have. So this is where you've got ordered scale points as well as equal distance. So the classic example is temperature. So the difference between 10 degrees and 20 degrees Celsius would be the same as the difference between 20 and 30 degrees Celsius. Time is another example, and test scores are actually another example. Now, interval data, one of the key characteristics of it is that it does not have an absolute zero. So a zero doesn't mean the absence of the thing you're measuring. In fact, it's actually just an arbitrary point on the scale. And temperature is a really good example because we all know that 0 degrees Celsius doesn't actually mean the absence of temperature. It's just a point at which we've decided to put the 0, and in fact, it means freezing for us, but it does not actually mean the absence of heat. Test scores are a little bit trickier to understand in that regard, but the idea here is that the score of a 0 that you might get on a test doesn't actually mean the absence of knowledge. It just means that the sampling of questions that were used to measure that knowledge resulted in someone potentially getting 0, but there clearly is the possibility that they have some of what it is you're trying to measure. And you can take test scores and convert them and standardize them so that the mean is actually 0, and then how far you are away from the mean would be indicated by standardized Z-scores. You may have heard of those before. The last type of data is ratio data. Now, ratio data is mostly used with physical quantities. 0 does mean 0, and some of the classic examples are weight, height, distance. So you can actually have the absence of mass, the absence of height, and 0 distance, or 0 monthly income. We don't really see this as much in educational research. When you're dealing with social science constructs, you're usually dealing with something where the scales are mostly either interval or ordinal. Okay, so that's some basic vocabulary about quantitative data, and it relates to measurement. The next thing I wanted to talk about was measurement error. So regardless of whether you're in the field of education, or in the hard sciences, physical sciences, a measurement always has some error. And what we're dealing with in educational research and social science research is that error is less easy to quantify and sometimes more of a factor in measurement than it is in the sort of physical and hard sciences. Error that is predictable is something we call systematic error, or bias. And this is the example of jumping on a scale, and every time you jump on it, you know that it's 5 pounds heavier than your actual weight. That's how it is for me every time. Every time I jump on any scale. But no, if you knew your true weight because you went to some amazing facility where they had the best scale you could possibly ask for, and you measured yourself and you came out as 125 pounds. I think that's even the weight that the textbook uses. And then you went home and jumped on your own scale and it said you were 130 pounds, and you got off and you jumped on it again at 131, and right around 130 every time you jump on it. That would be considered a systematic error or bias. And an educational example of that would be grader or marker consistency, consistently marking students somewhat more harsh than other markers. So in the context of, say, clinical OSCE examinations, where you've got multiple people coming and observing students perform their practice skills, you could have a situation where some of those markers are just inherently more harsh in how they grade students. And that would be something that if you set up, a data collection process well enough, you'd be able to quantify and say, okay, this person X, has a bias to be slightly more harsh, and we might want to adjust for that. So systematic error is actually a little easier to deal with. And there are methods that you can figure out, how much systematic error is in a measurement process. The other kind of error, which is unpredictable, is random error. And random error is what can lead to, a lot of unreliability, in fact, in measurement. So there are a lot of different factors that can impact how people respond to, say, test questions or survey questions. And those factors, those things that you aren't really considering that everyone brings to the table, are sources of random error. So we all differ in how well rested we are before we sit to take an exam, or we differ in our experiences to the extent that, if we're being asked questions about our beliefs, maybe social justice type things, there may be words that are slightly more triggering and lead to different types of response behavior amongst individuals, and those kinds of things that we aren't really aware of as potentially affecting our measurement can cause inconsistency and randomness in our measures. So whenever we measure anything, this is one sort of way to think about any measurement, is you've got a true score component, the actual value that if we could measure perfectly we would get, and then you have some error that's added to that with your measurement tool. And so when you are developing your measurement tools, you're trying to minimize the amount of random error especially, and if you can't get rid of the systematic error, then you want to try and quantify it so you know how that's affecting your measurement. The reason we talk about error is because it leads directly into this concept of reliability. So reliability in measurement is really just, again, connected to this concept of random error. So the more random error you have in a measure, the less reliable it is. And reliability is this idea of how consistent your results will be from use to use. So if I measure you once, will I get the same result if I measure you a second time? And if the more variability in that, the more random those results are, the less reliable your measure is. So essentially, reliability is an index of how susceptible a measure is to random sources of error. And we can increase our reliability. We can, decrease the amount of random error in a measure just by actually lengthening it. So adding a bunch of more questions to, say, a test or maybe a measure of motivation, adding more questions that are similar to the ones that relate back to the thing you're trying to measure will reduce the amount of random error, because repeated measurement is one way to, if you aggregate across a whole bunch of questions, you're actually strengthening your measurement and reducing the susceptibility of it to this random noise. Oh no. Oh, sheesh. I thought I was stopping recording for a second. No, I'm not. I'm still going, so I'll just keep talking. So I was saying how adding questions to a measure is how to increase reliability. But again, a key thing there is they have to be measuring the same type of thing. If you add questions that are unrelated to the concept that you're trying to measure, then that's not going to help your reliability. In fact, it'll make it worse. The text talks about all these different indices of reliability. And when you read in the literature, you're going to hear about, probably the most common one is Cronbach's alpha. And this is a number that exists between 0 and 1. So it ranges between 0 and 1. Values close to 0 means you have no reliability. You're just measuring random noise. Values closer to 1 mean that you have perfect reliability, and you can expect the repetitions of your tool on an individual to produce the identical results from measure to measure. So a lot of people will ask, what is a good number for reliability? It really does depend on what the tool is being used for. If it's for a high stakes learning type decision making thing, like whether someone gets into a program or not, then you need really high reliability. In fact, the higher the better. And most people won't accept anything less than 0.8 as a good enough reliability for high stakes decisions, like standardized tests or admissions, GMAT and those kinds of exams. When it comes to measuring social science constructs like motivation, and you've got maybe potentially small samples, and you're not able to really fully test the reliability of your instrument, then you can see things around 0.6 being acceptable. And in a classroom context, in fact, 0.6 with multiple exams being combined together by the end of a term, 0.6 would be considered probably pretty good for classroom assessment. In the context of research, though, we try to achieve as good of reliability as we can, and going through the process of developing good measures should allow you to achieve pretty good reliability. Okay, so talked about reliability. It's important for measurement, but reliability is actually just one piece of a bigger conversation about validity. Everyone loves validity. In the context of measurement, it's very similar to sort of research validity. We talked about research validity and how there were different types of research validity, and basically they were all sort of speaking to this big, broad question of, can we, number one, trust the conclusions that are coming out of a research study? And then there was that secondary question of, how far can we generalize those results? So when we're talking about measurement, which is something we do in quantitative research, we also have to ask ourselves, and this was one type of research validity that we talked about. We called it construct validity or measurement validity. We also have to go through a process of validation with those tools that we use. So it's this sub-type of validity within research validity. And a lot of times we talk about our measures being valid or invalid, and that's an improper sort of use of terminology, because tools aren't actually invalid or valid. It's how we use the scores from tools that can be invalid or valid. And so every time we go to use scores from an instrument, we need to go through a validation process. And that's just the idea of generating evidence to support our intended use. So if we're going to use those scores as an indication of how, how much confidence a person has, then we need to generate evidence that proves a few things. And some of the main things it should prove, or the main sources of evidence, are content related evidence. So we need to show that our measure in fact contains content that's connected back to the concept that we're trying to measure. So that you go through a process of having experts consult. You go through a process of conceptualization, which we're going to talk about next, and explaining how you actually created your instrument. And making sure that it's fully representative. It doesn't over-represent certain aspects of the concept and under-represent others. So content-related evidence is really just explaining why you think that the questions that are included in a measure fully sort of capture the concept. And you can ask experts to weigh in on that, and you can share that as evidence. You can also just lay out the process used to create the instrument, and that's how you generate content-related evidence. The next one is a fancy word for reliability, but internal structure evidence, which is evidence that the instrument is reliable, number one, and then number two, evidence that it measures the things you said it's going to measure. So sometimes our measures will measure multiple dimensions. And so you have to generate evidence that shows that there is, in fact, these multiple dimensions. And so you may have heard of things like factor analysis, where basically you look at how things cluster together, how questions group together using correlations. And if your factor analysis shows that the questions are grouping together the way you thought they should, then you've just generated internal structure evidence. And then also, if your instrument is reliable based on, say, Cronbach's alpha, you've generated internal structure evidence. So that's about like the way things hang together. Relationships to other variables is now taking the scores you get from your instrument and saying, these, because I'm measuring, some kind of construct like motivation to learn, it should correlate with things like how much time a person spends studying, for example, for a subject that you're measuring their motivation in. So when you get a score, you'll measure, motivation, and then you'll ask people to self-report how much time they spend studying or how much time they spend in their free time, learning this material. There should be a correlation between the scores you get on your motivation instrument and the amount of time people spend studying or the amount of free time they spend on that topic. So that's relationship type evidence. You use correlations. And I threw the words in convergent and discriminant because convergent just means, you're expecting a relationship. It could be positive. There's a correlation that's positive where higher scores on my motivation will correlate with higher amount of time spent studying. Or it could be negative. You basically would expect there to be some where my high scores would correlate with, say, lower scores. That would be a negative relationship. Those are both convergent type evidence. Discriminant evidence is where you don't expect to see any relationship at all. So I measure motivation to learn, and then I also measure, preference for coffee type. Like, do you like Tim Hortons or Starbucks? There shouldn't be a difference in motivation scores for people who go to Tim Hortons as there for people who go to Starbucks. There should be no relationship there, and if there is, then that evidence is kind of like not fitting what you would expect. So you generate relationship to other variable type evidence. Lastly, evidence based on response processes. So when someone is completing, especially a learning measure, they should be going through cognitive steps that are expected. And so, if they're working through a math problem, They shouldn't be able to figure out the answer by, using test wiseness, crossing out things because they got clues on previous questions or hints in the stem. They should actually be answering. So I'm on the last bullet here, evidence based on response. They should actually be answering by working through the steps, and they should be able to repeat those steps to you in by telling you how they work through the response process. We use think aloud data to generate this type of evidence. So measurement validity is just another place where we have to, basically support the argument that we want to use these scores to represent this construct that we plan to have it represent. Okay, conceptualization to operationalization. So conceptualization is a process of moving from general sense of the concept to actual rules and procedures that will be used to carry out the measurement. And there are 4 steps. So we go through a process. So we're at the stage of not really having a measure. And we're, no one's really figured out how to, say, for example, measure intelligence. And so the first thing we're going to do is, we're going to sit in a room together. We're going to share our images and indicators being the things we would observe that we think represent that concept of intelligence. So we're going to list them all on a giant piece of paper. We're going to, brainstorm a whole bunch of things we think represents intelligence. And then we're going to go through a process of grouping them into categories that seem to hang together. And those will become what we call the dimensions of our intelligence. So right now, all we have is, a bunch of sticky notes on a board that are grouping together. And we know that this is what we kind of collectively agree represents intelligence, but we need to put some words to it. So we're going to label, I guess, first of all, label the dimensions, and then we're going to write out a dictionary-like definition. You may not end up with dimensions. You actually may only end up with like one sort of common grouping of all these images you've come up with. But based on whether or not you do have these dimensions and whatever the groupings are, you're going to write out a dictionary definition. So this is just a couple of sentences that say, intelligence is a combination of a person's, various abilities that allow them to function successfully in, cognitive contexts. Something like that. We would just give a dictionary definition based on the images we've collected that links back, but doesn't really tell us exactly how we're going to measure things yet. The final step is to actually take the indicators, and now that we know, the things we need to observe, write out some procedures that will actually be used to do the observation of those indicators. And that's called your operational definition. So you've got the nominal definition and the operational definition. Okay, let's look at this in practice. So the way, a lot of people will talk about this is with a file drawer analogy. We all have these file folders in our mind that sort of hold all the images that are associated with different constructs that we use to communicate with each other. And, the one we're going to focus on for this example will be intelligence. So when we open up the file drawer, I have images like is good at math, has a strong vocabulary, can identify patterns quickly, is able to read social cues. Now that one seems somewhat unrelated to these other ones. Can reason logically. And so we would go through this process. We'd end up with hundreds of statements. Not hundreds, but we'd end up with a lot of statements that sort of capture what we think is representative of intelligence. We would group them off into subdimensions. And this is kind of the process that gave rise to some of the different intelligence tests that you see out there and the different dimensions that make up those tests. And then we would, you would come up with a written definition that would say, intelligence is a combination of a person's numerical, linguistic, and visual spatial abilities, along with their emotional intelligence, as well as their ability to reason logically. And so we've got, we've created a stronger understanding of what that construct is. We've given a framework that will help us identify indicators. Whoops. And then we would move to the final step of actually creating questions that map back to each of these concepts and tasks that we think will allow us to observe, these images, these indicators that we've defined. And then we would have our operational definition, which in the case of intelligence, there's so many different operational definitions out there. They're the actual tests themselves. So you can do the Stanford Binet as an example. And it's a combination of open and closed-ended questions where people are asked to solve different tasks. And there's obviously a lot more definition that goes into it. It has very specific rules about how scoring is done. And that would all have to be spelled out in your operational definition. So that's an example of conceptualization to operationalization. And then the last thing I wanted to cover was just the idea of the principles of good questionnaire design. These are kind of common sense. And, there's just one or two things I wanted to hit on here. I guess the one is this idea of a response set. So what is a response set? It's just a sort of a pattern that we fall into. So when we're answering a questionnaire where, everything is phrased in a way where you will agree with things, then, you'll fall into this response set where you're just acquiescing to agree. And so one of the things you try to do in good, measures design is you try to flip the polarity of the question so that people are having to either agree or disagree from statement to statement, and that it's not the pattern isn't predictable, but it sort of is allowing there to be some thought that has to go into answering questions. Most of these other ones I think are straightforward enough that I think you can sort of understand them from just reading them. I'd encourage you to do that. And this should give you a really strong foundation of understanding measurement, of quantitative constructs in social science research, educational research. See you next time.